Hi, my name is Martin. Welcome to the video about the history of drones. Drones, also known as unmanned aerial vehicles or UAVs, have come a long way since their early beginnings. In this video, we will take a look at evolution of drones and how they've shaped the world we know today. This video is based on a research paper titled Past, Present and the Future of Aerial Robotic Manipulators published by IEEE Transaction on Robotics in the February of 2022. For those interested, there is a link to that paper in the video description. We can distinguish three generations of drones. First generation, conventional quadrotors capable of applying forces to a wall while keeping flight stability, grasping objects and constructing cubic structures with an embedded arm with few degrees of freedom. Second generation, both indoor and outdoor operations, precise and effector positioning, and compensation of perturbations. Third and current generations with fully actuated platforms, multiple arms, GNSS-free navigation capabilities, onboard SLAM, onboard perception without markers, off-board real-time planning with control awareness, and onboard reactivity and planning. There are 7 types of platforms: helicopter with unidirectional thrust, ducted fan with unidirectional thrust, parallel propellers with unidirectional thrust, tilted propellers that can be fully actuated, over-actuated, or omnidirectional. Then we have tiltable propellers, which can have multidirectional thrust, or omnidirectional or over-actuated. Then we have multi-rotor morphing and multi-platform systems that can be either ducted fan, parallel propellers, and tiltable propellers. These platforms can have different interaction tools. There is a rigid link, gripper, a passive link, which is very similar to a rigid link, but attached to the vehicle by a passive joint, such as a cable or a wire, or articulated arm. These tools can do the following physical interaction tasks: pick and place, point contact, pulling, pushing, sliding, peg in a hole, or manipulation. Most drones have one arm. 2 or more arms can be useful for grasping long objects such as tubes, valve turning, and to replicate human abilities. As an interesting fact, one of 2 arms can be used as a position sensor holding some object, while the second arm performs some operation on the object. When it comes to control of the aerons, we can distinguish 4 types. 1. Decoupled. Independent control of manipulators and propellers, not suitable for high acceleration scenarios. Coupled, where whole system is treated as one entity, and that is very useful for dynamic cases. Then we have partially coupled, where control of the aerial platform and the manipulator are independent, but the controllers exploit the information provided by each of the systems to estimate the interaction and improve performance, typically in terms of positioning accuracy. And decoupled flatness-based, where each degree of freedom is controlled independently as in a decoupled controller, but the full system dynamics is considered via a feed-forward term, computed thanks to the differential flatness property of some aerial manipulators. Multi-body designs can do the following: aerial grasping of objects directly using their bodies, aerial operation in cluttered environments via serpentine motion, large-size robots that can do aerial manipulation free from classical issues such as short operation time, low payload, and difficulty in control and sensing, and articulated flying characters in amusement parks. There are 3 phases of aerial manipulation operation: navigation from takeoff position to the proximity of the workspace, ensuring collision avoidance and reactivity in case of unexpected obstacles, approaching to the desired operation position with higher accuracy, manipulation with accurate position and interaction control. Phase 1 and 2 consider collision avoidance and accurate SLAM in GNSS denied environment. In phase 3, Object detection, tracking and localization are required. Localization and mapping is usually based on GNSS, but accuracy degradation due to satellite invisibility prevent UAVs from autonomous operation. Alternative approaches are based on environment perception. Absolute 3D localization and mapping can be performed using LiDAR, stereo cameras, and radio range measurement. Ultra-wideband time-of-flight sensors are applied to compute position of a receiver on long distances. They can provide position estimation with accuracy of 50 centimeters. On medium distances, LiDAR provides better accuracy and reliability. At small distances, stereo cameras can be applied to fuse point clouds from LiDAR and cameras. Additionally, ICP with IMU can be combined, optimizing the joint error. It can be implemented in real time with moderate computational cost. In object detection, visual cameras are the most popular sensors. We can distinguish two different tasks. 1. Detection of objects at a certain distance, about few meters, based on features like color and shape, templates of the target and classifiers. 2. Detection for grasping and manipulation, high accuracy, about few centimeters, mostly based on markers. There are 3 planning levels. There is a mission planning, which is a general high level. Then we have individual tasks. And then the lowest level, that is motion planner, that computes the trajectories. It is common to decouple motion planning of the platform and the manipulator to simplify the computations. Firstly, algorithm plans trajectory for center of gravity of the platform, and then algorithm plans motion of the end effector. This approach is simpler, but it has some drawbacks like inefficiency in time and energy, as well as obstacle avoidance. Very small robots are subject to disturbances, particularly the outdoor wind. Additionally, it is very difficult to consider all unexpected objects and forces acting on a robot. Autonomous reactivity should be based on perception from range sensors, computer vision, and force torque sensors. Let's move on to challenges. First, there is time of flight and range. Current time of flight is about 10 to 40 minutes, too short for many applications. Increasing time of flight involves new batteries that are denser and lighter, as well as more efficient motors and computers. Current solutions are perching. In some situations, robot could perch on support structure like pole or cable to save battery. Hybrid aerial-ground platforms that on longer distances travels on the ground and flies if ground transport is not available. Hybrid fixed rotary wing platforms that has 2 flight modes. Fixed wing for low precision long distance travel and rotary wing for takeoff and precise movements. Morphing and bio-inspired approaches, inspired by birds and insects, changing between the low drag and high lift configurations. Flapping wings aerial vehicles are called ornithopters. They can switch between gliding and flapping to save energy. When it comes to accuracy, it depends on the sensors that are limited by wind and rain. These effects are difficult to model because they are unpredictable. Modeling and control of aerodynamic effects increases the accuracy, but cancellations of all perturbations is difficult, so perching or holding a support should be considered. Accuracy depends on the sensors limited by wind and rain. These effects are difficult to model because they are unpredictable. Modeling and control of aerodynamic effects increases the accuracy, but cancellation of all perturbations is difficult, so perching or holding a support should be considered. Current EROMs require human supervision. Increasing autonomy should positively impact reliability, but it requires powerful computers and many sensors, increasing power usage and weight. Variability in lighting conditions limits perception. Perturbations are unavoidable, deviation will always happen. Computers will need to provide reactivity based on the environment's perception. Adaptive compliance should be a feature of future EROMs. In conclusion, the history of drones is a fascinating one, filled with innovation and progress. From their humble beginnings as radio-controlled aircrafts to the advanced drones of today, they have come a long way and will continue to shape the world we live in for years to come. Thank you for watching, and if you have any questions, please leave them in the comment sections below this video.